It's not unzipping. Okay. Export DSCH. Wait. Okay, fine. Good evening to all. Hello. Whether my voice is audible? Yes. Good evening. Very good. Fine. So now, welcome back for this hour. And as we have started with yesterday, yesterday I have talked about the introductory part about VLSI, their design flow. We have discussed about the back end, front end, this type of things we have discussed yesterday. Today, what I have planned over that, today I'm going to, okay, today I'm going to showcase you how can we use certain EDA tool. Okay, so here I'm going. So till now, okay. So yesterday we are talking about a certain EDA tool, and I also discussed about some of the vendors, like how are the vendors are utilizing the teams, sorry, utilizing the softwares. Also, we have mentioned the name like Cadence, Synopsys, then AMD. Those are the certain vendors. They are purposefully providing certain software. Okay, so now those softwares are sometimes licensed one, and sometimes it comes with the certain open source. Okay, uh, but we know uh, okay, but we know that to share the softwares, the softwares are always do not the open source. The all the high quality softwares like the Cadence software, which I have mentioned last yesterday, those are providing the tool for digital as well as analog. Similarly, the synopsis to provide digital analog, but those are coming with very high payments. Okay, so currently, what I plan for today, I would like to showcase you one of the softwares, like how the software can be utilized for the circuit designing, right? Now here, today in my our WhatsApp group, I have shared one of the software which you must be watching that, the namely it is DSCH. Okay, are you finding that? Yes. So now just access that software. It is a zip file which I have shared, a very small software. It is open source actually, which is provided by the Microwind. Okay, Microwind is one of the industry which do offer the software for digital as well as analog. So currently I have shared one software namely DSCH in WhatsApp group. Just download the software, and if you have the laptops with you, you can do the on the parallelly you can do the certain accessing or simulation world. So this is a software which you are watching now, software DSCH. So first of all, you need to let me start here only. First of all, the DSCH software, once you download it, simply open for extract to DSCH. One new folder will be created by unzipper. Okay, now here it is a very nice software. Why I like here that because here we don't have to do any type of installation. It automatics create one application file, and those application file can be used for the learning purpose or evaluation purpose. Now here it creates one new folder here, software DSCH 2.6. Once you went inside, here we have the this is a my existing. We don't have to install this software. We can work it without installation. So now if I'm going to under type here, you will find very one application file. Okay, this is my software DSCH2. So today I have planned that like I can showcase you how to use this software to for the circuit designing for digital as well as analog background. So here, if you let me just simply double click on it, DSCH2, that is our application file. It will come up with black color background window. So it's a very small software. Hardly it will come around some 500 to 700 KB of software. So easily we can access it. Easily can you download it. Once, okay, first of all, what is the status now? Does everybody have installed the software, download the software? Because to see, so my planning today is that if you're going to work with the software, no, you will get some better idea how it is the importance of the circuit designing and how the industry are also working on the same similar type of existing. So meanwhile, you can just simply download your software. Simply you need some internet connections. Here I can demonstrate you how the front view of this tool. The front view of this tool is the DSCH2 digital schematic. Now here we have the option of file. Okay, option of file in the top ribbon. Here we have the option either create new file, save as. Here we have one word is called select foundry. Okay. So foundry is one of the it is a word generally used for the technological background. So which foundry would like to design our circuit? So foundry is like yesterday talked about process engineers. So whatever the designer going to make GDS file, those file we need to send for process. Now during the process engineer, they will map the GDS file according to the instrument they will use according to technological standards. So the technological standard is like CMOS technology, 180 nanometer or 90, 45, 32. So those type of technological parameters are coming up with one PDK file that is called process design kit. So first of all, here we are going to discuss about select foundry. Under the foundry, here they will there are certain rules like still talking about the steps. Here we have DRC, LVS, RCX. Those are binded with certain rule. Which rule we are going to follow? So in this automatic, it will create in this location where we have the some technological rule which I want to use, like which tech file, CMOS 0 0.6 tech, 8 CMOS 80, 120, 180, 25, 250 nanometer, or by default we can take any one. So say let's a system authorize to choose any one. Let's see, I'm going to use CMOS 180 nm tech file. Open it. It means our currently designs are mapped or all the designs are correlated with the 180 tech file. Okay, here we have option either we can go for the monochrome or you can go for the color background, so it will come with automatic. Here, okay. Now most important symbol is the library, symbolic library. This symbolic library have the some component which are inbuilt. Like we have the certain logic gates. Okay, here we have certain logic gates which can use where we can use our logic gate for the circuit designing purpose. Because yesterday talked about digital design flow, the logic gate are the basic symbol, basic horse which can use for the designing. Like we can make the all any type of logic gate. So either we can go for schematic based or programming based. So today schematic is our introductory part. Okay, today we are going to discuss about introductory part how the schematic can use for the designing some circuit. So here the symbolic library, what are the available? We can use it and we can simply drag and drop. Like I can the NAND gate, simply drag and drop with the help of mouse. We can place anywhere. Okay, guys. So sorry, I have got one call urgently in between. So here, what I discussed out till here, what I have shown you the here how I can use some DSCH tool for the circuit designing. So for circuit designing, here I have shown you like a drag and drop. Here we have the input. We can go for the output. Here we have the top ribbon. Here this symbol I can use as a wiring. Here I can use the wiring of the certain symbol. Simply I can make the connection anywhere, and we can able to make some circuit design. Here we have the symbol for simulation. Okay, this is a symbol for timing diagram. Now, if I would like, meanwhile, you people are able to download the software. I can show you very small thing here. How I can use this symbol. This is a symbol for cut. So we can cut the wire, extra wire if I have. Now here we have the option of this button. How to provide the input, we have the choice. Either I can provide the button or we can provide the clock. These are the two options I do have. Or we can provide the keyboard, hexa board to provide the input. Okay, suppose I am going to provide the button means manual input, clock represent here automated input. Now let's see if I am going to take one clock as a input. Okay, now try to complete the connections with the help of wirings. Okay, it has been connected. Now here I can join it directly or we can make the wires. Now here we have the output. To display the output, we have option of light. I can go for the lighting symbol. I can connect it. Okay, this is one of the circuit diagram which I have shown as a NAND gate. Okay. So now here if you'd like to, by default they have got the name, but if I want to change it, simply double click on the symbol. Suppose if I'm going to change, double click on it, it will display the name. What is the name you would like to have? Suppose I'm going to input, I'm going to write input A. Here we have the option what you want to showcase, display the pin number, title, switching delay, or leave it default. Okay, input A. Okay. Name clock to B. Okay. Why it's not changing? Okay, sorry. The name I have to change from here. So I'm going to write the name out. Here I'm going to make the name A, and here I'm going to provide the name as B. Now if I want to make faster clock or slower clock, we can just change the input here. That how much time it will remain for logic 0 and time to remain on logic 1. Simply press OK. So this is our input and output has been biased. Now here we have this green color button that's for the run simulation. Yesterday I talked about the run simulation. Simulation is a process of verification, functionality verification. It means the circuit has been designed. We need to apply some input and we have to check the corresponding output, correct or not. So this process is called simulation. So now we have applied the input. Now if I'm going to press the symbol of input, now it will show because of the clock. Here I have the option. I can control the simulation. Either I want to make slow speed or we can make high speed. So this is my simulation control. Okay, now we can, here we have the option. So it will go for the very slow. So we're going to make somewhat faster. So now whenever the input 0 and 1, so based on the truth table, it will display the output. On the same time, here we have option. I can show the pin state. The pin state means here it will show whatever the inputs are supplied from the clock, input A and input B. So according to the NAND gate, it will generate corresponding output when LED is on, when LED is off. Depending on 0, 0, 0, 1, it will make the corresponding truth table LED on or off. Afterwards, if your simulation is performed, we need to understand the waveform. This is a timing diagram. Open this timing diagram. The circuit which we do have simulated, the same thing I can convert into the timing diagram. So with timing diagram or timing waveform, this is the response output generated from the circuit. Okay, so now here you can imagine that here input is 0 when the waveform is coming, or logic 0 or logic 1. So when B is coming at the 0, so it's going to make here some combination 0 0. Output is high, that is the 1. For the 1 and 0, output remain 1. 0 1 is 1, and 1 and 1, output going to remain 0. So now my output we have generated from this circuit and output of the NAND gate, that is the same. If both are correctly matched, then we can understand, yes, our simulation is correct. Okay, the simulation is correct, so it will generate here the, okay, it is going to generate here the correct output. On the same time, here it in the bottom, you can find here what is the maximum current and maximum power consumption. That's also given to us according to the technological standard. Okay. So here you have the view all. It will show the complete waveform, how much time we have simulated. Here we have option to provide current. So total current, maximum current, average current, and the power consumption based on the technology. It is given pre-calculated over here. So now we can close it. So this is the one of the very small software. It's the open source actually, and here it can use for the learning of this schematic design. Fine. Okay, now what is the status back? Come to our room. So whether are you able to access this software? Not connected. Why? Screen not visible. Yes, I'm joining back. I think there are some network had got fluctuated. So meanwhile, you people just simply download this tool and try to unzip it so that we can work in parallel. Fine, I think so. Now I'm audible. Okay, yeah. So now we are discussing about the word called critical path. The critical path, it represents which path is the longest and which is having the maximum delay. Now here critical path, since I have taken only one component, critical path cannot be computed. So it will show here the multiple paths. If you have from multiple input and multiple output and which represent longest path, that is your critical path. And practically, I should say the total propagation delay of the circuit. This is the delay associated with critical path. It means, first of all, longest path is the critical path, and delay of this longest path is the total delay of the circuit. Okay. So this was the one of the very nice tool given by the microwind, how to convert a program. Okay, convert a program or convert a program into Verilog schematic based design, and we can learn about the timing waveform. Okay, so now this is a very simple design. I am not going to save this one. If I'm going to make, if you want to save it, you can go for save as. You can save via some name. Else, I'm going to make the new file. Do you want to save? No. Okay, make the new file now. Okay, now can I have some input from your side? Are you people able to access this tool now so that you can do parallel programming? Yes, very good. Okay, now let's see. Let's see. Let me go for the some advanced type of circuit designing. Now, first of all, what I like to say is here that if I want to design some circuit diagram where some Boolean equations are given, like suppose some Boolean equations are given. Now we need to simplify it. For simplification, you know well, we have the K map or we have the Boolean algebra, simplify it, minimize it, convert it into circuit diagram. Now, what I'm going to discuss here that uh, shall I assume that people have knowing about decoder and multiplexers because multiplexer is the one of the smartest circuit in our VLSI world. So, can I assume this word? Like you are comfortable with this word, multiplexers? Yes, very good. Okay, today I'm going to start with the word called multiplexer. Okay, today I'm going to start with the word multiplexer. How we can use multiplexer for our designing? Like we know multiplexer, it is a we have the multiple input, some number of selection line, there is a one output line. Now, whenever we want to implement some function using multiplexer, now here we have to think about which is our input, which can be our output. So now suppose if I'm going to take one example of a simple function of 1247, that is my mean term, that is my SOP expression 1247. So can you guess what is this number 1247? So in the digital electronics or digital design, this is a very interesting number. Mean term is 1247. That represent the equation is A XOR B XOR C. Okay. So A XOR B XOR C that represent either some equation of full adder as well as difference equation of full subtractor. So this is a way this is a very simple way to understand some equation of full adder as well as difference of full subtractor. So now here the question would like to say implement this multiplexer. Okay, sorry, implement this equation 1247 with the help of multiplexer. Okay, so suppose I'm going to write some s equal to uh, M, that is my main term, 1, 2, 4, and 7. These are the four things we should like to implement via mux. So now, how to do that? Okay. The very first, here I would like to showcase one shape. Take one diagram for multiplexer, in which I know multiplexer, we can go for 2 into 4 into 1 multiplexer or 8 into 1 multiplexer. So here 4 in, first of all, I'm going to take a 4 into 1 multiplexer in which I have two input. Okay, here we have the two input and here we have the two input line and the selection line. So if I'm going to take here the 4 selection line, first of all, let me draw this diagram complete. Okay, here I'm going to take here the 4 input line. Now out of the 4 input line, I need to have here the 2 select input. Here we have the 2 selection input which represent here S1, S0. And here is again there is a one output line. So this represent one architectural diagram of 4 into 1 multiplexer. Okay, so here I'm going to write the simple word 4 cross 1 mux. Now, whenever I would like to make some particular equation, so how to implement it? The very first, my suggestion is here, try to write into the variable format. What can I write in variable format? S equal to, can I write here? 1 means we can write 0, 0, 1 if I 3 input. So I can write here A dash, that is whole, that represent the complement, B dash C plus, let's zoom it somewhat. So first of all, this is my variable format for the sum equation 1. For the 2, I may write here 0, 1, 0, A dash, B, C dash. For the 4, I can write 1, 0, 0. And for the 7, I may write here ABC. That is my 1, 1, 1. So this is my variable format. So what I did here first, I made the main term write into the variable format, complete a canonical expression. Afterwards, out of ABC, any two can be used for the selection line. Suppose if I'm going to write input A and input B for the select input, and here is my final output S. Okay, here we are to make the multiplexer input S. Now, what can be the input here that going to represent here C? Okay, so in the C, we are going to write here the equation simply by means of comparing. We can do that. So here we know that when AB, this position represent for the 0, 0. Okay. Afterwards, the next position that represent here for 0, 1, here represent for 1, 0, and it represent 1, 1. That is the option for 4 into 1 multiplexer. Okay, so now now look at here when AB 0, 0 that represent A bar B bar in the variable format. So just compare it. Do we have A bar B bar in this equation? If yes, what are the third input that represent here C? So here we have to write simply C, that is our input. So out of 3 input A, B, C, any two can be select input and the remaining one that is my primary input. So here I have got A, B, C is my primary input. Now next input 0, 1. 0, 1 in the variable format that represent A bar B. So A bar B do we have over here? Just look at here. A complement B is there. Input is C bar. Okay. Similarly, here we have 1 0 that represent AB bar. So AB bar I may write C bar, and for AB I can write here C dash. So that is my implementation of any function 1247 with the help of multiplexer. So what we did that, like A B C bar C, that is my input. Okay, now that is my, on the paper we have drawn this specs, in the paper we have drawn this circuit. Now try to simulate it whether my circuit is correct or not. For that I need to take the help of this tool. Okay, the same thing I would like to draw with multiplexers. So here you can think about, here you can go for basic component. Here we do have analog component also, which can use for analog purpose. Now here you can think about what are the component available. Here we have the multiplexer, but here I have 2 into 1 multiplexer. I don't have here the in the inbuilt component we do not have 4 into 1 multiplexer. Okay, so what to do here, this not be possible. So we need to, first of all we need to think about 4 into 1 multiplexer to be designed. So 4 into 1 mux is not available, so we can here we other option is 5 input gate, 3 input gate, or multiplexer. So what can we do? We can design from the our own component. First of all, if you remember the symbol diagram for multiplexer, or you can use this 2 into 1 multiplexer to make 4 into 1 multiplexer. After that you can provide it. Okay, so here I can use this topic, so I can use this 2 into 1 multiplexer. Again I can use this 2 into 1, minimize somewhat. Okay, and here I have got 4 input that we require, and here I can use again 2 into 1. So now I assume that you people knowing about how to make 4 into 1 multiplexer with the help of 2 into 1 multiplexer, right? So here I am going to define, that is my, this output is the input for here, this output will be input for here. Select input, I can define the name. Here the, okay, this is not able to change, leave it. Take the wires, I can provide, this is my select input. Here I can provide on this select input, and this select input must be sorted. Delete this wire. Okay. So I have got two selection line. So here I have defined there is a one input A, there is a one input B, and here I have defined four input C, C bar, C bar, and C. Right? So here with the help of buttons, this button I can use to define the input. I can define this name is A. If you want to provide some specific color, you can play with that. You can provide from here, or you can keep default one according to your choice. Now here I have to take one more input B. I'm defining some other color. Now here I have to take one LED, that is for the output purpose. Just complete the circuit first. Now from the, we have take one third input C. I'm finding the name C. Okay, so now what are the input we have provided? Here I have provided first input is C. Second input I have provided C bar. To provide C bar, I will take one NOT gate from our library. This is our NOT gate. Can I rotate it? From rotation, it is, we can, yes, we can rotate it from here. Or we can stretch it somewhat longer. Now just complete the connections. So first input provided C, second input provided C bar, third input is also provided C bar. So I can join from here itself. So I have got input C, C bar, C bar. This input must be C. I can take from here. That is our complete connection. Okay, if you wish, you can save file. You can save it. If you automatic, it will save with example.sch extension, or you can provide your own name. It's your choice. I have to make some. I want to make it separate so that you can touch each other. Yes. Now this is my complete circuit diagram which we have made 4 into 1 multiplexer, and it is going to implement 1247. Now from here, if you want to change the name, I can provide it. Now after that, the same way, we can do the simulation, run simulation. Once I simulate it, right now it is showing output is coming. What are the value actually you are showing here? Okay, the value you are showing here, it is a constant 0 right now. No inputs is there. Sometimes you are getting, somewhere you are getting, watching here the 1, somewhere you are watching the X. Okay. So X represent here don't care. Remember the word in the digital world, we have the don't care. Generally in the K map, we are representing. So right now, practically, we are not providing any input since I have used the button input. So by default input is 0, 0 is providing. Now when providing here inputs, I think there are some connection issue because we should not get X value over here. Yeah, because I think there are some connection issues. Let me take the input again. Okay, so now are you able to find the same type of issue with you? And I think we have the, let me delete this part. Let me try with the automated clock input because I don't know why this is getting this issue here. Okay, sorry, it was a C. You try it first. Okay, because it getting sorted over here. Yes, I got the issue. The issue arises here because of the short circuited. Let me delete these wires. Because when we are bypassing it, actually I would like to connect over this terminal. Okay, I want to connect this select input should be connected to this input. When we are passing through it, it getting here the joint over here. Because of this short circuit, it creates certain issues. So as a solution, uh, we should not go for these connections. Okay. What I do simply, I did here that I have simply mirror it. I simply mirror the multiplexers. Okay, once I mirror the multiplexer, so both the select line come to each other. So now we can make these connections. Because I told you we have the open source tool, we have some limitations. So because whenever the wire is crossing, so they are getting sorted to each other. Otherwise, we have to take the crossing of avoid the crossing of wires. Okay. So add a connector, fine. So otherwise, we can make this type of output. So let me delete this part. I not think so it will work. I can take the one button input from here that I have seen the C. I can take one selection line for this in selection line for here, and I can take one select input for this A. So here we have A, that can be the C, and here it can be the B. Okay. Now if I'm going to open this multiplexer, now let's see if I show pin name, if I off it, okay. So it is show name property. I removing it. Only keep the pin numbers. Okay, it will show here the piece fine. So now if I'm going to simulate it, now it should work according to our requirements. So right now I'm getting all output 0 because my input providing 0 0 0. Since I have taken the button input, for the button input I am getting manually I have to feed the input. Once I provided here input on this one, it will go like it will going to showcase which multiplexer input will pass. Okay, so now these are our choice. Like from the here manually we have to provide inputs and we need to check accordingly our output will appear. So that is the like circuit designing, like how the input going to flow and how the output going to flow. My output becomes 0 or 1. If I make it 0, now what can be the output? Which input will be passed according to multiplexer? Fine. This was the one of the easy demonstration. I hope so you are work on the same. Now if I'm going to open this timing diagram, so here you can imagine, you can analyze it. So this is the option, I can zoom it somewhat. And after zooming it, here you can find it according to the this is a simulated waveform. So in the waveform, what I'm watching that when we providing the input, when the waveform it as lower or higher, that represent 1 or 0. So 0 0 0, our output is 0 0 1 0, output is still 0. How we are reading the waveform, that you need to understand. When a waveform is 1 0 0, that is the randomly I have made, so it is going to perform the output is 1. Now here I should highlight here, like here we our input is coming 1 0 and 0. So at this point our inputs are appearing, but my output will appear or this terminal. There is a one very slight gap. There are some gap from appearance of input and appearance of output. That represent here because of the delay. propagation delay, that is depending on the technological file which I have used. Next combination 1 0 1. Here I have got output is 0. Now 1 1 1, output is 0. 1 1 0. For the very small time it make one combination, output is 1, because after that this input change 0 1 0, output is 0. So how the inputs are appearing on the same way I will get simulated waveform. Okay. Now, I hope so you are understanding the situation, or whatever I'm trying to explain. Well, is it okay? Fine. So is it fine now? So what we have seen up to here. So in the bottom you can find it, visualize it, how the power going to, how the timing waveform, how the fluctuations are there. So here I have shown you the maximum power consumption is 1.41 milliampere, average power 0.07, and power consumption is 0.053 milliwatt. Okay, now in the bottom here I have shown a small power waveform. The waveform, if I'm going to zoom it from here, and if I'm going to scroll it, here it is showing this type of power consumption. Let me zoom it some more. Okay, so now what we can what understand, what is the understanding coming from? What is the understanding from this waveform? Let me start from here. Okay, so now actually if you have learned about the CMOS VLSI, you must be knowing the in the CMOS technology there are two type of power consumption. One is the static power and one is the dynamic power. That part I will discuss in few later on. So power consumption is static power is when there is no change in the input. The power will consume because only of the circuit. Like in this diagram, the power is remains constant. But when the inputs are changes, there is a high power consumption. That represent because of the dynamic power. Okay. So because of the dynamic power, what I am watching here that there is a high power consumption. Whenever the more input change, there is a more power consumption. When the lesser input changes, low power consumption. So practically, this is the one situation depending on input and output. So that represent here the complete timing analysis. Now understand, hope so understanding this part. Okay, now from here we have option. I can close this simulation now. I will get back to circuit diagram. Now here we have the option to make the Verilog file. So automatic it converts the Verilog code for the schematic drawn. First of all, in every Verilog program start with module. We have to define all the ports in the module name and end with end module. After module, we need to define the ports, primary input, primary output. Now, how the circuit we have made, on the same way I have to design. First of all, I took one multiplexer. The name is mux, and how the wiring has been done. That need to understand. S W1 W2 B. How the wiring has been done. For that we need to learn. We will discuss about Verilog coding style. Similarly, three multiplexer, one NOT gate, simply write a program for it and it will map the circuit. Now in the center we have given the certain number 13 or 23 that represent here propagation delay. So NOT gate, there is a maximum delay, system defined. Here they got the net listed, fine. That is a critical path. So now this is the one of the way we can add it or we can learn it about multiplexers. Fine. Now suppose if you want after this design, all are everything has been tested. Now we can create a symbol. Go for the file. There is one option is called schema to new symbol. Now schema to new symbol means I can make our own symbol for this design. If you want to make vertical or if you want to make horizontal, we can rotate it accordingly. Okay, so here it will map this type of design, which pin number I want to make, ABC, pin position number, left or right. Keep it by default. It will show this location where it's going to store. After that, simply OK. Once I are going to make this OK, it means a symbol has been saved. Okay, I'm saved it. Symbol has been saved. Suppose if I'm going to make it save as, I'm going to save it some name. Like suppose I'm going to write some name is lab. Now I'm going to make a symbol for it. Schema to new symbol. Simply I'm going to make a new symbol. Okay, the name is lab. Okay. Now if I'm going to make the new file, what is the use of this symbol is, now suppose I want to call my library, that is called instance. So I can go insert. Here they will provide what insert means, user symbol. Which user symbol I want to insert, we have to provide the name like lab.sch. Open it, so automatic this lab will come in our picture. Okay. That is user symbol. If I want to insert lab.sch, if I want to insert lab.symbol, then only symbol will appear. If I'm going to minimize it first, so this is my complete schematic, and if I want to insert only a symbol for it, then I have to write the word symbol, insert lab symbol. So only symbol of the component will appear. So in this symbol, what are there? Only we have primary input and primary output. The primary input is ABC and S. So all these multiplexer, NOT gates, these are inbuilt into this box. So what to do? Simply apply input over. Simply apply here the input and I will get here the corresponding output. Okay, so if I'm going to test it over here, simply I'm going to test it over here and take here one LED as a output, make the wirings. I should get similar type of expectation. Okay, now when I'm going to simulate it, so okay, because this is a clock input I have chosen, so for the clock input, it will come automatic. We don't have to provide the input. It will come automated output. So, but in the clock input right now, all the clock working on the same time. So we have to make differential time, different times so that I will get the all combination. Now once I'm going to simulate it, now I will get corresponding output 0, 1, 0, 1 variable depending on my inputs. Whenever red means binary 1 input, blank means there is no output, binary 0. Now I can pause it or simulate it. Now see the waveform, I will get similar type of output over here. So that is the one of the very interesting fact or learning about this software. How can we use this program or how I can use this software for the learning of VLSI. Okay. I hope so you are comfortable up to here, or if somebody has any query. Okay, so as you are telling that you people have this software installed, now continue with the same, continue with your designing part. So now designing with logic gate is very simple and very easy. Designing logic gate is very easy. Like digital electronics, you have learned about in your BTech life, also second year or third year, whenever this course was there. So now here I would like to attract your attention about some advanced component that is my these two transistor NMOS PMOS. Okay, so NMOS PMOS these are the two very specific one which can transistors. Because yesterday also I talked transistors are the basic building block for complete electronics. All the component is made up of only transistor. Okay, so now right now the symbol which I am using these two symbol I would like to use N channel MOSFET and P channel MOSFET that is generally used for designing the logic gate. Like with the low power because yesterday I talked bipolar transistor used for high speed and low power transistor that represent for the MOSFET technology, right? Okay, everyone. So now let me start with some new thing here. Now I would like to take how do we use this symbol NMOS, PMOS for designing some circuit. So I will in our next session I will discuss about the working operation of the MOSFET, how to define the MOSFET working operation, VI characteristic that is separate part. Today I want to simply demonstrate how to use this NMOS PMOS for designing the circuit diagram. Okay, so now if I take this, simply drag this PMOS and simply if I drag here one symbol for NMOS. Okay, so this is a symbol for PMOS where we have the three terminal. The central terminal is the gate, source, drain. For the N channel, gate, source, drain. Now here they are showing representing some name W and L. That are actually defining here the aspect ratio of transistor. Okay, so W and L, W represent width of a channel, L represent length of the channel. Remember the word when I have taken the word select foundry. The foundry I have chosen the 180 nanometer. So they have got L equal to 0.18 U, which is 180 nanometer. If I simply change my foundry, if I'm going to change my foundry, let's see, I'm going to make 60 or I can go for like 25 to 50 or there's some smaller 120. Now if I'm going to make the foundry delete this component, let's take the new component again. If I take one PMOS, it will see here L going to change. So L represent here technology. Okay, the technology either we can go 180 nano, 180, 45, 32 nanometer, that is for FinFET transistor, 40 nanometer, or even though GA, FET, or we're talking about 1 nanometer. So this nanometer actually represent length of technology. The length of technology represent 120 nanometer. If I open it, here we have the option. I can change the W value or length value. It is editable over here. Here you can show the name source, gate, drain, how they have defined. Okay. Now, which here they have also given option either I want to go for standard high speed or high voltage, which category of transistor we want to use. Okay, let's leave it. So now after that, I remember yesterday somebody I have drawn the not transistor level of the inverter diagram. So try to implement one inverter diagram with this software. Okay. So as we know, for PMOS, we need to keep PMOS on the top, which will define the pull-up logic. NMOS we need to keep in bottom, which will define the pull-down logic. Okay. Now here we have the option power supply and ground. These two I can use to define the pull-up and pull-down. Okay. So I can take the wires and simply I am going to join with that. Okay, this is the one of the diagram for CMOS inverter. Okay, I have made here length 360. Let me make the somewhat smaller 120. Length will be same. W becomes the W of PMOS must be twice of the W of NMOS because of their threshold compensation. So W of PMOS must be twice than W of NMOS. Now we have to take the one output. We know the output should be taken from the source and drain. Here if I'm going to write the pin name, it will show here source, gate, drain. If I open it, show the pin name, it will show here the source, gate, drain. So drain must be common where from the drain terminal I can take one output. And similarly gate must be common from where I can provide the input. Either I can take button input, which is the manual, or we can take clock, which automated. Okay, this is my input. Now this is the definition or designing of CMOS inverter, which is equivalent to NOT gate. Hope so you are doing the same. Okay. Now afterwards, simply simulate from here. Is run simulation. Now here it is showing the option. Right now input is 0. Input 0 means 0 has been going to the PMOS upper part, 0 going for NMOS. Now what it shows? This represent in the center they provide one region, this rectangular path region where I am showing the switching connection. When in gate input 0, this PMOS upper path it become closed switch, but this NMOS this represent open switch. And we know the current rule of Ohm's law say current will flow only in closed path, not in open path. Okay, so here since this is the closed path, power supply, it is binary 1 that is connect to this up to here we have got binary 1. So my output was connected to this drain terminal, I have got binary 1. But this NMOS was off, open path, so it is not going to connect with ground. So in this condition, my output is pulled up because my output is going upward or generating the high output, upper input. So in this case, this PMOS provide a path through which output will be pulled up to VDD. Okay. Now if I'm going to change my input, it provided the one input. One input means what it says. PMOS becomes off, open connection, but NMOS become closed connection. Now closed due to closed connection, what is learning now? This going to ground. This output is connected to drain. So now here is the open connection. Current cannot go upward in the open path. Current will go into the downward closed path. So here output is pulled down. So what is the message here that this NMOS provide a path for the pull down network to the ground. Okay, so after that I can off this, make this timing waveform. Here you will show this type of curve. Okay, this type of curve. Since I have given a long way, let me simulate it again. So since this is my binary manual input, here I have to press every time to provide manual input and we can check NMOS, PMOS. Okay. Now I can draw this timing waveform so that you can understand it will work as the inverter. Okay. Here, okay, in this case we are not able to map here the transistor diagram, so only logic gate that is option there. So here this is the option. We can make here one inverter, CMOS inverter, which is the opposite. Output is complement of the input. So this inverter going to act as NOT gate. Okay, so now based on this understanding, so what we are going to discuss, what we are going to learn, outcome of this message is when I am going to provide input, when the input equal 1, input equal to, let me start from here, input equal to 0. Input 0, what we mean the PMOS. I should write PMOS on and NMOS off. Okay, when the input is 0, PMOS become on, NMOS become off. On means closed switch, off means open switch. Similarly, I will write one more. If you wish, you can write this statement. If when we provided, when I'm going to provide input equals 1, we can write PMOS becomes off and NMOS that become on. Okay, these two are the very interesting facts that we are going to learn in our next session. Also, I will take this, repeat this topic, but always remember this: when the input is 0, PMOS on, NMOS off. When input is 1, PMOS off, NMOS on. So from here we can verify this simulation. Okay. So this is our NOT gate inverter. Now if you wish, you can make the same. We have the option to create Verilog file. Now in this Verilog file, what we are finding that here you will have the same type of programming style, input module, input and primary output. But here this type, this is called NMOS PMOS. They will call NMOS PMOS from the library. And this type of modeling style is switch level modeling. Okay, it represents switch level modeling because yesterday I talked also transistor act as switch, right? Transistor can act as a switch. So here, because of this terminology, when we are going to design a circuit, digital circuit with the help of transistor, then the Verilog, the separate a unique modeling style that is called transistor active switch, right? So here I have shown you this software. You have the access on it. Now try to explore, try to design some different type of circuit and try to convert in Verilog code so that you can able to correlate how the programming and schematic both are working in parallel. So here we have some other option like lookup table. Here we have marks. So here we have the pad input, pad output, 8-bit display, so numeric numbers, inductance, mutual inductance, capacitors, resistors, op-amps. You may explore it based on your requirements. Okay. And here we have the programmable switch matrix. Generally, we are using programmable switch matrix for the programmable interconnection point. When you are talking about PLA and PAL, programmable array or programmable combination, then this option is there for FPGA. So right now these are sufficient for learning to us. Here we can use this type of switch registers and these types of categorize to design the circuits. Okay. I'm going to now take the new file. I'm not going to save this file. Okay. Now think here what to do here. I hope so you people are doing this because it is remote access, so I cannot watch on your screen whatever you are doing on there. So I'm expecting that you people must be working in parallel and trying to learning these softwares. Okay. Okay. Now right now. Okay, so here I can show you, I'm going to design one circuit diagram with the help of NMOS PMOS. Simply try to understand or try to tell me which type of circuit it is. I'm going to take one PMOS, one NMOS. Here I'm going to put one NMOS. I'm going to take four PMOS, four NMOS. Okay. I'm expecting that you should tell it which type, what is the name of this circuit diagram. So I've taken four PMOS because of the circular symbol on the gate. That is a symbol for PMOS. I can flip it. I can flip it from this symbol so that, okay, I have got this type of connections. I'm going to flip this transistor and I'm going to put one transistor like it and I'm going to flip it. Simply either you can make with me in parallel, or I'm going to make this type of connections, and here I will take one ground for pull down and I will take one VDD for supply pull up. Okay, this is my one input I have connected like it. Shall I delete this part? I will take one input to be connect down, and I can take one input to be connect down to a second transistor over here. Okay, so this is my circuit diagram, complete circuit diagram, in which I took two PMOS and two NMOS. So can somebody just give me the reply on the chat window, which type of connection it is or which type circuit diagram it is? NOR gate. No, Shivam, yes, it's a NAND. Very good, Habib. This is the NAND gate. How to identify this is the NAND? Okay, this is a NAND gate because here we have to understand connection wise. If I'm going to make connection in series, or if I want to make, we're going to make connection in parallel. Very good. PMOS in parallel or NMOS in series. That's going to define it is a NAND gate or it provides the NOR gate, right? So if you're knowing about it, very good. Okay, so now since I'm going to make it, so I can provide this type of input A and B, and I can take one output LED from the drain terminal and simply simulate it. So when I'm going to simulate it, since here you can showcase how the switch going to on or off in parallel or in the series. So they are going to make here the connection of 1 or 0. Now simply pause on it. Now you can check the timing waveform. This is a symbol diagram for NAND. Okay, I have got only two options since I have to make this automation. I have to make somewhat slower. Now again simulate it, this part, and after simulation we're going to make this waveform. So here I can have the all possible combinations, so we can verify 0 0 this 1 1 0 that is the 1 0 1 it is 1 and 1 1 it is 0. This is the expectation or output of the NAND gate. Okay, so in this way we can able to design this type of circuit diagram, and we can think about how to make the different connection with the help of transistors. Same way, you can export this program into Verilog and you will get the, according to my circuit connection we have made, it will map into the Verilog coding. This is switch level modeling, PMOS 24 output. First of all, they have to map the output port for PMOS 1 output port, input from the VDD, then clock. That is my drain, source, gate. That is my port mapping. Similarly, for NMOS gate W3 that represent the wire. Wire is my name of this connection between source and drain. So every wire, every terminal must have some defined name. Let me define as a wire and try to make this come all the connection according to the NMOS PMOS logic diagram. So when our designing is in the format of NMOS PMOS, that is going to say is the switch level modeling. Okay, that's going to make here switch level modeling over here. Now if I want to the simulation information, it will show here the test bench. How to write this test bench over here. Okay guys, so this was the one example like which I have discussed about how to discuss with a NAND gate transistor level diagram. Okay, on the same way, you can explore this tool again. So try to make the different type of circuit and symbols. So you will get over the different type of learning. If I'm going to open it in our library, in the library there are certain inbuilt diagrams. So from here you can have this symbol connection. If I'm going to make, this is my two transistor XOR gate. Okay, two PMOS, one NMOS, so it's three transistor. So that represent three transistor XOR gate. How they have designed it with the help of how to put PMOS, how to put NMOS. Now let's see if I'm going to simulate it, you can verify whether it's working as a transistor sometimes or okay, wait. Let me change this waveform. Okay, so since in this case it can going to define as a XOR gate with the because XOR gate equation A bar B plus AB bar, I need at least 14 logic gate, 14 NMOS PMOS. But here the with the playing of W I put PMOS 2, here NMOS is 1 with the playing of W and this type of connection that represent here the PTL logic, pass transistor. So this output going to connect with input, this input connect with the drain terminal of the output, not on here. One thing again I can highlight here, in this case there is no VDD, no ground, the powerless groundless logic that represent the pass transistor logic. Now you can waveform, you can find it. So are we able to get here this type of we are getting this type of waveform that represent this sort of connection. So when the both input is 1, output becomes here for it be 0. That is my requirement. But for sometimes it become here the don't care undefined output. Okay, if I'm going to zoom it all. So what is showing that when input is 0, 0, it becomes 0. 1, 1, I should get here 0. So we are getting 0 for there, but there are some conditions, some limitations. Okay. Similarly, you can explore some more about this tool. If I'm going to showcase you what are the different type of inbuilt components or logic gates are there. Like here we have 7 segment register, 4 LS138 traffic light, 8051 with microcontroller, CLA. A CLA is there, or schematic and symbol adder 4 schematic that I want to showcase how they have made the 4-bit adder, most popularly known as the ripple carry adder. Okay, so here input ABC, here output sum is going to display on the BCD number, and here we have the carry going to flow for next. Since carry is propagating as a chain, so that is known as the ripple carry adder. Now you can simulate it when input is 0 and 0, output is 0, no carry. When 0, 1, output is 1, 1 and 5, it is 6, carry not required. Now here D plus 6, I have got 1 carry plus 3. That is our carry is going to flow up to here. So now this is the hexa display, hexa keyboard that can use for the providing some larger input up to F, that is my hexa display. Fine, so that is the one of the way you can explore this more learning, and if you would like to showcase one more with the transistors. On the transistor level, they have made adder signed bit, 4-bit test. Here we have amplifier, differential amplifier. That is the more interesting fact. How they have made differential amplifier, 2 PMOS, 2 NMOS. Provided the VP, VM, do input, how to get here the output. Okay. Simply going to run over here, you will get, but here we have, the output becomes here act, because here we have to provide the input. Input we have to provide from sine wave. So we can take the sources, digital sinus. Okay, the digital sinus it can use to provide sine wave. Now the sinus, if you open to double click on it, it will show sinus 1, sinus 0, where delay, fan in, fan out, everything to be defined. So which type of sinus we want to use. Sinus 1, sinus 2, loads 0. So this is the one of the way like when you are exploring more, or in voltage, we can provide voltage source, that is my AC. Yeah, amplitude is 1, phase is degree. So here we have option to provide the resources, and here we have provided the piecewise linear model. In the piecewise linear model, there is a one very interesting thing. Here we have to define time and value every bit. Which type of waveform I want to make. Okay, that we need to define. Like time equal to 0, value 0. Time equal to 0, value 0. Time 2, value 1. Time 3, value. So it will make one square waveform where x-axis is the y-axis will be the bit, either 1 or 0. Okay, so that's going to make here the sine wave, that is sorry, square wave, as a PWL, piecewise linear model. So we may use it depending on our requirement or purpose, which type of input to be used, and that's going to define here our requirements. Okay. Fuse, simply going to make here, I told you programmable option, we can make here the fuse connections. Okay, so this is a very simple tool actually. We have the very simple tool which I have shown you right now. Here we have option to design digital circuit as well as CMOS based circuit. We can simulate it, verify it nicely, but limitation is we cannot do analysis. I'm talking about analysis means we cannot make the what is the power report, what is the area report, delay report, noise, gain, bandwidth, stability, margins. When talking about the aspects, specification, so those features are not available this open source software. For that, we have to go for EDA, standard EDA tool. But those are the very difficult to access everywhere. So here, for circuit designing, circuit schematic entry, as well as simulation, we can explore these things, or we can explore this type of software. So at least try to go for these examples. If you want to make clock divider, if you want to make this type of circuit learning, so it will make this type of output to you. Okay, here I have, so here you will get some nice understanding or learning from here. So the example which I have displayed right now, this is going to define here critical paths. Here we have the one AND gate, one AND, 1, 1, 0. That is my primitive of NOT gate. Here we have the equivalent, that is the my XOR. Here we have AND. Here we have greater than or less than, greater than or, that is my OR gate. So different type of components are made, and every component have different delay. Now what is learning from here, that it is going to discuss which path is faster. It will display output. We call it critical path. So which path? The path going to define. I told you longest path that define here the critical. So now to provide the 1 1 1 input, I'm getting here the both output 0. Okay. To provide both output 0 here. So now it is going to say in this case we can have here the output for how much time we are going to get here the output. So in the waveform, okay, in this waveform here we have option like add currents, timing is not appearing for this case. Yes, timing is here. So now here we can watch here when input has been applied 1 2 3, output 1, which out both output is coming together. So here we can find it here, this output coming first, this output coming later on. That's going to define here the combinations, how to define the word path. Okay, so that is the one of the today one of the discussion which I have planned for today, to hands-on session with some software. Okay. Okay, if somebody have any query up to here, please go ahead. If you want to save this type of design, simply go for print. It will export into PDF. Okay, now I'm close this type of design. So this was the today class, today learning which we have. Now next, when I'm going to meet next time, I will try to highlight the content related to transistors. But can I have some input from your side? What are your what are your levels? So should I go for the MOSFET based explanation, more details like the how the architecture. Okay, so can I have from your side some input? What are the expectations for how much more basic I need to cover? Can I go for the architecture of the MOSFET, like how the drain, source, gate, how the channel is going to create, what are the VI characteristic? No, that's very nice. So because at what level I should start, that also I should go for that. So accordingly I can plan myself. Yeah, because I say this because otherwise it will be the repetition part for you. Okay, so can I go for the afterwards? Can I go for circuit designing? Like I go for the complex type of complex circuit designing via the NAND, sorry, like CMOS based circuit designing for complex equations. Yes, CMOS. Fine. So as the input I have received, I will not cover the basic diagram, the high characteristics, threshold. These are the, I assume that you people comfortable with that. So I will try to cover from the CMOS based designing, like how the CMOS based circuit designing and what are there some advanced type of questions related to that. Okay. Fine guys. So now let me close by this today this session. I hope so today you have enjoyed well. Okay, guys. So thank you for today, and let me close the session for today here. and we can give you the input on our WhatsApp group itself. What are the new things we are going to discuss and how we are going to plan for next time. So thank you all.